This is the last video covering a test for the convergence of an infinite series. We've covered the divergence test and the integral test. We've covered two comparison tests, the comparison test and the limit comparison test. We've covered the alternating series test, and we've covered the ratio test. We're now ready to do the last test, which is actually one that only applies in a very narrow set of infinite series, but it's relatively easy to implement. And when you need it, none of the other tests generally tend to work, except possibly the ratio test. We're going to take a look at what the ratio test requires, and we're going to see that the ratio test and the root test have the same conclusions. So the two tests that start with R, you're looking for rho again. We saw that again when we were looking for the limit comparison test. And we'll see that the conclusions for the ratio test and the root test are the same. They're not the same as the conclusions for the limit comparison test. So you want to be sure that you know which test you're applying and what the conditions are. Let's take a look now at what the root test says. The root test again starts with some unknown series where we don't know too much about the a sub n's. Now, it's possible that the a sub n's have some negative terms. It's possible that they're all positive. It's possible that some are zero. It's possible that none are zero. We don't know anything about a sub n. There are no requirements on this. But we do have some kind of summand where the whole thing is being raised to some power that depends on n, either n or n plus 1, n minus 1, maybe even n squared. So we're raising the whole summand to some power dependent on n. Then the root test says to go ahead and find rho, where rho is the limit as n goes to infinity of that root of the absolute value of the summand. So it's the nth root of the absolute value of the summand. Then we get the same conclusions that we got with the ratio test. If rho is 0 or less than 1, then the series will converge absolutely. So no matter how you rearrange the terms, you get the same value for S infinity. If rho is greater than 1, some finite real number, or rho is infinity, then we know that the infinite series will diverge. If rho is equal to 1, like the ratio test, the root test is inconclusive. Now, if you get an inconclusive result, such as rho equals 1, you probably don't want to use the ratio test, because when one of these tests gives you an inconclusive result, the other tends to give you the same result. So in that case, you want to go back and use the integral test, as long as the terms are eventually not negative, or you want to use a comparison test. Again, a comparison test is the most powerful of all because it has no restrictions on it. It's not requiring that the terms be eventually non-zero or non-negative. It's not requiring any of those things. But it is, again, one of the most difficult to prove. So when do we want to use the root test? Well, like I said, we want ones where we have exponentials, the entire summand being raised to some power that depends on n, to the 2n power, the n plus 1, n minus 1, even n squared power. That means that the absolute values of our a sub n is some kind of sequence being raised to the nth power. Then we can simply take the nth root. So if we're taking the nth root, that means that we're taking the nth root of the absolute value of a sub n, which is the nth root of this sequence b sub n raised to the nth, and then the nth root undoes the nth power, and you just get b sub n. And then you're evaluating the limit of b sub n, which is a much simpler thing to try to do. We're going to again skip the proof for the root test, though you can find it in the textbook if you want to follow it along. Let's go ahead and start with our examples. We have 4 examples for the root test. Again, it doesn't get used as often as the others, but when you need it, boy, you really need it. Now, looking at this particular series, how do we know to apply the root test? Well, we can see that the summand consists of the ratio 3n plus 2 divided by 2n minus 1, all raised to the nth power. So the entire summand is being raised to a power that depends on n. That's when you use the root test in a nutshell. So we want to go ahead and apply the root test. Now, if we're looking at this, we might have some difficulty applying the divergence test. So we're going to directly apply the root test. And in fact, we'll see that the divergence test would have told us that it was inconclusive. But again, we're just going to start and we're going to apply the root test from the get-go. So we have the limit and we want to take the nth root of the absolute value of the summand a sub n. Now, as it turns out, because my n is starting at 1, 2 times 1 minus 1 starts at the value of 1. So the denominators are going to be strictly positive for n greater than or equal to 1, and so will the numerator. And because the power doesn't affect the sign, only the base does, then we know that in fact all of these are going to be positive. So we'll be able to drop the absolute value relatively quickly. So we have the limit here as n goes to infinity of the nth root of the absolute value of 3n plus 2 divided by 2n minus 1 to the nth in the absolute value. Now, if it is not the case that all the terms are already all positive, you're going to have to chop off the head and set those aside, and then take the series that starts at a later n value, and then you will be able to drop the absolute values. So we need to drop these absolute values so we can take the nth root of the nth power. And that is, of course, going to lead to the following expression, where the limit is still as n goes to infinity, and we have the nth root of 3n plus 2 divided by 2n minus 1 raised to the nth power. Now, you know the nth root is the 1 over nth power, and so this undoes that, and we're left with the limit as n goes to infinity of the sequence 3n plus 2 divided by 2n minus 1. Now, we can apply L'Hopital's rule because this one has form infinity over infinity, and when we take the derivative of the numerator and the derivative of the denominator, the ratio of the two derivatives, this is going to lead us to the following value. The limit as n goes to infinity of 3/2, which gives us 3/2. Now, 3/2 happens to be larger than 1, and that's a problem because the conclusions for both the ratio and the root test, that to conclude that it converges, it's got to be between closed 0 and open 1. And that's not. And that means that by the ratio test, it diverges. Now, would we have gotten the same thing if we had applied the divergence test? And the answer is yes, we would have. By the ratio test, the series n equal 1 to infinity of 3n plus 2 over 2n minus 1 to the nth diverges. So again, we see that it gives the same results as we would have gotten if we had applied the divergence test. The problem with the divergence test is that we can't bring the limit inside because the power also depends upon n. So we would have had to apply some kind of special algebraic trick, but basically it results in something that approaches 3/2 to the n, which of course being exponential goes to infinity. So again, the divergence test would have failed. All right, now let's take a look at what the sequence of partial sums plotter looks like on this one. So if we get this one going, we can see very quickly by looking at the sequence of partial sums that the black dots look like they're growing to infinity. And that's because the sequence itself, the values in the sequence, the values inside the series, the orange dots, are not approaching 0. Remember, we said that if the tail of the sequence doesn't go to practically 0, roughly 0 for every term, it's not possible for the sequence of partial sums to converge. And we see that this meets the result that we found previously. Let's now go ahead and look at example 2. In example 2, we would again have a little bit of a difficult time probably trying to evaluate the divergence test. We know that this can be written slightly differently. We could rewrite this instead as the series from 1 to infinity of 1 minus 1 over e to the n raised to the nth power. But again, if we were to take the limit as n goes to infinity, this is going to give us 1 to the infinity, which is, it's going to be kind of difficult to prove. We would have to exponentiate it and then take the natural log of the expression. So it would be a very difficult one to do with the divergence test. But if we can use the root test instead, so we're going to use the root test now, and we get rho is equal to the limit as n goes to infinity of the nth root of the absolute value of a sub n. So this is going to be the limit as n goes to infinity. And make your radical, make the n really fit inside that notch. And then we have the absolute value of 1 minus 1 over e to the n, all raised to the nth power. Now we have to think about whether or not those are all going to be positive and for what values they are positive. I know that for n greater than or equal to 1, e to that power is also going to be greater than 1, which means 1 divided by that number is less than 1, which means 1 minus that fraction has to be greater than 0. So I know that this is strictly positive, and a positive power raised to any, or a positive number raised to any power is still positive. So I know I can drop the absolute values, and that then allows me to take the nth root of something raised to the nth power. So now I've got this nth root of 1 minus 1 over e to the nth power to the nth power again. And the nth root undoes the outside nth power. And this is going to give me the limit of the sequence n going to infinity of 1 minus 1 over e to the n. Now, I know that the limit of a difference is the difference of the limits, right? I can split this up and I can do it in different ways. So once I split this into two limits, this becomes the limit as n goes to infinity of 1, which just gives me 1, minus the limit as n goes to infinity of 1 over e to the n, which I know the denominator goes to infinity. So this one goes to 0, which gives me a 1. Oops, that's bad. Why is that bad? Well, when rho equals 1, it's inconclusive. So what does this tell me? Well, it tells me absolutely nothing. I do not have any idea as to whether or not this might converge or diverge. I would need to apply some different kind of test. Maybe I could try the integral test, or more likely I would try some kind of comparison test. But basically at this point, we're stuck on this one, all right? This did not work. Probably using the ratio test would lead to the same result of getting rho equal 1, so it would also be inconclusive. So again, we can see here that it doesn't always work, but we can try it, and most of the time it will work. Let's take a look now at the sequence of partial sums plotter for this example and see if we can get an intuition for what might be happening. Aha. So when we're looking at this, oops, sorry about that. I was trying to close some of those open windows. There it is right there. Looking at the sequence of partial sums plotter and the sequence itself, it looks to me like the sequence is not going to 0. Well, if the sequence doesn't go to 0 by the divergence test, we know automatically it must diverge. Now, this is not a proof because this is only showing me the first 30 values. It doesn't show me the entire sequence. So it's not a proof, but it does give me an indication that probably this series diverges. And we can see the sequence of partial sums is just, almost linear in form and going to infinity. So that also gives us an idea that probably this series does in fact diverge. Let's now go ahead and take a look at the next one. This is example 3. On example 3, I went ahead and put the picture down here so that we didn't have to consider it. Again, trying to apply the divergence test would be very difficult here. We have a tower function, n to the 1 over n power minus 1, and then the whole thing raised to the nth power. Applying the divergence test would be difficult, if not impossible. But by looking at the sequence of partial sums plotter, we see the sequence of partial sums in black, and we see the terms of the sequence in orange. It does look as though the terms of the sequence are dropping to 0. That's not a proof. The proof would be evaluating the limit, which I probably can't do. But it does at least give me an indication. It looks like these sequence of partial sums are approaching some value near maybe 0.3. So it looks like it may converge. So I'm going to go ahead and use the root test. So when I apply the root test on this particular problem, so I get rho equals the limit as n goes to infinity of the nth root of the absolute value of a sub n, which gives me the limit as n goes to infinity of the nth root of the absolute value of n to the 1 over n power minus 1 raised to the nth power in absolute values. Now I have to ask myself, is this going to produce positive values? Can I drop the absolute value? Well, I have to think about what n to the 1 over n is. And I might actually go off somewhere and actually plot it so I can see what it looks like. But you can see that it actually is graphed right here. It's the function f of x, x to the 1 over x minus 1. Oops, do I have an extra? Oh, no, raised to the x power. And you can see right here that it does look like the function is strictly positive. So that means that I can then drop the absolute value. It's not a proof. Again, I would have to think about n to the 1 over n. I know n to the 1 over n is going to be a positive value, but I would have to think about whether the square root of 2 and the cube root of 3 and the fourth root of 4 minus 1, are those going to give me positive numbers or not? And the answer is yes, they do. So I can drop the absolute values and continue to solve for rho. And this gives me the limit as n goes to infinity of the nth root of n to the 1 over n power minus 1 raised to the nth power. So the outside nth power is now gone. And we get the limit as n goes to infinity of n to the 1 over n power minus 1. And again, this is the limit of a difference. So then I can take the difference of the limits. And when I take the difference of the limits, I have the limit as n goes to infinity of n to the 1 over n minus the limit as n goes to infinity of 1. So this just goes to 1. So in essence, I need to evaluate this first limit, n to the 1 over n. I need to figure out what that's going to. Now I know the values are strictly positive because n starts at 1 and goes to infinity. So this is strictly positive. Positive base raised to a power is always going to be positive. But as n goes to the infinity, this becomes infinity to the 1 over infinity, which is infinity to the 0th power. That's the form we have right here, which means that I need to apply the exponentiation and the natural log of what's inside the limit. So I need to apply the exponential function and the natural log function so that I can use that to pull the power of the tower function down to the line so I can get my hands on it. So we're going to hang on to this minus 1 for a while, and we're just going to focus on that particular limit. So we're looking at the limit of n to the 1 over n. So this down here becomes e to the limit as n goes to infinity of the natural log of n raised to the 1 over n power. So again, we apply the natural log and its one-to-one inverse function e to the u, and that undoes each other. So it, in essence, isn't changing anything. They're one-to-one functions. This does let me pull the power on n to the front. So in the next step, I'm going to have e to the limit in approaching infinity again, 1 over n times the natural log of n. Maybe put that in parentheses. Now, as n goes to infinity, 1 over n approaches 0. So this has the form 0 times. Well, as n goes to infinity, the natural log function also goes to infinity very slowly, but it does get there. It's just super slow. So we have the form 0 times infinity, which is an arithmetic indeterminate form. So we've gone from infinity to the 0 to 0 times infinity. We never move natural log. So all I need to do really is slide that n into the denominator under natural log. And that will fix the form to be one of the two basic forms, 0 over 0 or infinity over infinity. So now I have the natural log of n divided by n. And the natural log of n as n goes to infinity has the form of infinity. And the denominator also has form infinity. So I have infinity divided by infinity, which of course is one of the indeterminate forms. And so now I can apply L'Hopital's rule to basic form. So I'm going to apply L'Hopital's rule at this stage. So I have e, I still have the limit as n goes to infinity. I take the ratio of the derivatives. The derivative of natural log is 1 over u du dx. So I get 1 over n. And then the derivative of n with respect to n is just 1. But in the denominator, all I have is the factor n, and the derivative of n is 1. So now I have 1 over n as the power on e. So I have the limit, or e limit as n goes to infinity of 1 over n. Now, when I look at that particular thing, what I end up with as n goes to infinity is 0. So this gives me, of course, e to the 0, which is equal to the number 1. So now I need to come back up here to where I was a minute ago. Actually, it's all still up here. And I can take that result and put it in place of that first limit. So then after I follow all the steps in blue, ... I get that this becomes 1 minus 1, which equals 0. In other words, the value that I get for rho is 0. Now I had to go through and evaluate this one separately, but I did end up with 0 as the value of rho. And that means that, of course, it does converge by the root test. So I get that this does converge, which was what I suspected. So then I have my final result, right? Therefore, by the root test, the series from n equal 1 to infinity, making sure I'm doing the right one, of n to the 1 over n minus 1 to the n converges absolutely. We don't know what it converges to, but we know that it converges to some finite real number. We can take a certain number of terms to approximate it. Remember, the head has most of the values because the tail, the values are practically 0. So we know that we can estimate it with the first n terms, and the more terms we use, the more accurate it becomes. Now let's take a look at the last example for the root test, which is example number 4. It looks like we don't need all that extra space. So I'm going to delete the extra space. And let's take a look now at this one. So we have n to the nth over 3 to the 2n plus 1. Now, I'm suspecting maybe, I'm not 100% sure, but I'm suspecting that this one probably diverges. Why would I think that? Well, I'm thinking about the divergence test. I've got a tower function in the numerator and an exponential function in the denominator. And I know that tower functions grow on an order of magnitude larger than exponential functions do. Now, I can't apply L'Hopital's rule because I don't have a way to take a derivative of a tower function. But I can apply the relative growth theorem, which would tell me that this limit of the sequence is going to go to infinity, which would tell me that the series diverges. But to prove it, I'm going to have to use the root test because I can't use L'Hopital's rule. I could claim the relative growth theorem if your professor will let you do that. But if not, then you'll need the root test. So we're going to do the root test right here. And this is going to give us, I'm not sure if I'm looking at the right one here. So this is going to give us rho. And we need to take the limit as n goes to infinity of the nth root of the absolute value of a sub n. But remember, every time we've done this, we've had the summand in parentheses raised to some power of n. And I don't have that here. I don't have that here. So what am I going to do? How am I going to do the nth root if I don't have it all raised to the nth power? Well, I'm going to have to come over here to the side, and I'm going to have to work on my summand so that I can get the whole thing with some power that depends on n on the outside. So I'm going to have to work on the expression for the summand. So I have 2n plus 1. Well, I know automatically that one thing I can do is I can pull 3 off and write it as 3 times 3 to the 2n. That's a little bit closer, all right? So now I've got the nth power here and the 2n power here. And then we use another rule for exponents, which says that if I have one base and 2 powers, I multiply the powers. So I can write this as 3 squared to the nth, all right? Again, I've got one base 3 and 2 powers on it, the 2 and the n. So that would give me 3 to the 2n, which is back to what I had before. But 3 squared is 9. So I think that I could rewrite this as n to the nth over 3 times 9 to the nth. And now I've got 2 things being raised to the nth power. So I can go ahead and put them together. And this would give me 1/3 of n over 9 to the nth power. All right, now it looks like I can maybe apply the nth root to this. Now it is going to give me the nth root of 3, but 3 is a constant. So this should be something that I will be able to do. So now we're going to come back over here to our definition for rho, and we're going to substitute this new expression. And of course, since n is greater than or equal to 1, we know that a positive raised to a power is going to be positive, and the exponential 3 to a power is always positive no matter what. So we know that the terms are strictly positive. So we'll be able to drop the absolute value very quickly. So we have the limit, n is approaching infinity. We have the nth root of the absolute value of 1/3 n over 9 to the nth power. Inside the absolute values, we know they're already strictly positive, so we can drop the absolute value, and we get n approaching infinity of the nth root of 1/3 times n over 9 to the nth power. Now, you need to split this up. You can only split radicals across multiplication and division, but we have multiplication. So I can split this into 2 radicals, and I can think of this as the limit as n goes to infinity of the nth root of 1/3 times the nth root of n over 9 raised to the nth power. And in fact, with limits, I can take the limit of a product and make it the product of limits. So I can split the limit across those as well. Now, what is the next thing that I want to do? Well, 1/3 to the nth power is 1/3 raised to the nth power. And we know that 1 to the nth power, of course, would end up being 1. So we're going to rewrite this in a different form. We have the limit as n goes to infinity of 1/3 to the n. And then we take the nth root of the 9 over n to the nth power, which gives us 9 over n, right? The next thing we want to do, of course, is rewrite the expression 1 over 3 to the nth power as 1 over 3 to the nth times n over 9. And then we have to think about what this is going to approach as n goes to infinity. Now we have the form of infinity over infinity. The 1/9, of course, is a constant. We can factor that out of the limit. And then we have 1/9 times the limit as n goes to infinity of an algebraic function n over an exponential function 3 to the n. Now we can apply L'Hopital's rule one time, where you can claim relative growth theorem. Exponentials outpace algebraics, and it will drive it down towards made a mistake. Back up a little bit. This isn't the 1 over or the n power, it's the 1 over n power. So I was looking at this going, wait a minute, that says it converges. All right, so this is the 1 over n power. All right, so I'm not real sure because I've got 3 to the 1 over n power. If it were 3 to the n, I would know it would drive down to 0, but I don't have 3 to the n. I have 3 to the 1 over n. Okay, well, that's something a little bit different. So I'm not 100% sure of what's going to happen here. So what do you think might happen here? What might be your next step? How would you evaluate the next step? Well, you have to imagine what's happening as n is going to infinity. So as n is going to infinity, imagine what we'd get if we plugged it in. We would have infinity in the numerator, and we'd have 3 to the 1 divided by infinity in the denominator. This is as n is going to infinity. So you can't really plug in the value infinity because it's not a value, it's a direction. But we can imagine the limit approaching this, but 1 over infinity would go down to 0. So this seems to indicate that it would approach something like 1/9 times infinity over 3 to the 0, but 3 to the 0 would be 1. So this looks like it would go to infinity over 1, which of course then tells me that it goes to infinity. So I would tend to think that this must diverge. And because rho is this infinite value, then we can say that the original series is going to diverge by the root test. Therefore, the infinite series from 1 to infinity of the tower function n to the n divided by the exponential function 3 to the 2n plus 1 diverges by the root test. And let's take a look at what it looks like on the sequence of partial sums plotter so that we can see whether or not what we got matches what we see on the picture. So when we're looking at this particular one, you can see that at first, the orange dots do look like they're going to 0, but then notice after about 6, they start going away from the axis. They're actually climbing away. So that as n goes to infinity, the limit of the sequence is not going to 0, or doesn't seem to be going to 0. A picture's not a proof. And of course, the partial sums, notice they start out close to 0, but then they also begin growing without bound. So again, our picture does reinforce what we found with the root test, that that particular series diverges. And this concludes the video on the root test. We're ready now to put everything we've learned about convergence of a series together and start studying power series, which can be used to approximate and even give exact values for some of our transcendental functions like e to the x, natural log, trig functions, inverse trig functions, and so on. I hope you'll join me for the next series of videos covering Chapter 6, Power Series.